Hello everyone, welcome to Reactify Labs. Today we will be doing another Leetcode hard problem and it is called merge k sorted lists. Okay, so as the name suggests, you are given k sorted lists and you have to merge them. Okay, so let's understand with an example. So there is a list L1. Okay, there is a list L2 1 3 4 and there is a list L3 2 6. Okay, so if you see individually these all are sorted. So now we have to merge them. So what we can do is we can merge these two lists and we will get a new list, right? So it will be 1 1 3 4 4 5. Okay, let's say this list is called list 1 2 and there is a list L3 already 2 6, and then we merge these two, and so we will have L1 2 3 equals 1 1 2 3 4 4 5 6. Okay, so this is our list. So if you see, what we did was we have, let's say, L1 L2 L3 up to Ln lists. So what we did at this time was we merged L1 L2 first. Okay, then we merged L12 with L3, so we have L123. Then we merged it with something else, maybe L1234. Okay, and eventually we got L1234n, right? So what is the time complexity of this? So if we assume that we have total, let's say, k lists, right? The question says that we have k lists. Okay, and let's say on an average each list has m elements. Okay, average. Okay, because they will have different number of elements, they can have different number of elements, they can have same number of elements as well. So the average is m. So total number of nodes is k times m. Okay, let's name it n. Okay, so if you see, we have total n number of nodes. So in that case, if you see, when you merge L1 and L2, okay, so L1 has m elements, L2 has m elements, right? For merging them, you need time complexity of order of m, right? Because you have to compare each of them, and since they are sorted, that's why order of m. Then you start merging this with this has size now L12, for this size is 2m. Okay, and you merge it with L3 which has size m, so again it is order of m. So basically you perform order of m operation k times, so your time complexity becomes order of m times k. Okay, which is also order of n. Okay, so the question is, can we do better than this? And also if you see, at this time our space complexity is order of 1. You can say why order of 1, because when we are merging L1 and L2, we are creating L12, right? So it is taking extra space, so it cannot be order of 1. But no, this is not the case. While merging L1 and L2, we can merge them both in L1 or we can merge them both in L2. We are just naming it L12. Okay, so we are not using or creating any extra new space. So we are just using the existing nodes, and since they are nodes only, right, we are not creating also any new nodes. So we are just rearranging the nodes. So the space is constant actually at this point. So the space complexity is order of 1 and time complexity is order of n. So the question now is, can we optimize this? Because this will work. Okay, if you look at the constraints given, so the constraint says k can be maximum 10 to the power 4. Okay, k can be 10 to the power 4 and m can be maximum 500. So time complexity order of m times k is basically 5 times 10 to the power 6, which is much less than 10 to the power 9, the number of operations a computer can do in 1 second. So that's fine, it will work, okay, it will work. But the question is, can we do better than order of n? Can we do better than linear time? So the question is, can we do better than that? The answer is yes, we can do better than that. But how? So for that, let's say we have L1, L2, L3, L4, L5, L6, L7 and L8. For simplicity of explanation, I have used the total number of lists, which is a power of 2. Okay. So instead of merging L1, L2 and then merging it with L3, L4, what if we do something like this? We merge L1, L2, then we merge L3, L4, then we merge L5, L6, then we merge L7, L8. Okay. So if you see, we get L1, 2, L3, 4, L5, 6, L7, 8, right? And the size is now order of still m, but now the size is 2m, 2m, 2m and 2m, right? Now again, if we merge these, we get L1, 2, 3, 4 and here we get L5, 6, 7, 8, okay? And when we merge them again, we get L1, 2, 3, 4, 5, 6, 7, 8. So if you see how many merges we did now, we did 1, 2, 3, 4, 5, 6, 7 merges, right? So 7 merges, but if we had done this, if instead of this, if we had done this L1, L2, L3, L4, L5, L6, L7, L8, then how many merges we would have done? 1, 2, 3, 4, 5, 6 and 7. We would have done 7 at that time as well. So what is something that we optimized here? Did we optimize anything? The answer is no, we did not optimize anything here. Okay. Because if we keep on doing this thing, we will keep on having the same number of merging that we do. But where we are saving ourselves is, if you see, for the first one we merged m and m, for second we merged 2m and m, for third we merged 3m m, for fourth we merged 4m and m, for fifth we merged 5m and m, for sixth we merged 6m and m, and for seventh we merged 7m and m, right? So if you see how many operations we did, 2m, 3m, how many comparisons basically, 4m, 5m, 6m, 7m, 8m, right? Okay. Oops, sorry, it happened. Yeah. And here, let's see how many we did here. So here we compared m and m, again m and m, again m and m, and mm. So we did 2m here, 2m here, 2m here and 2m here. Okay. Now we did 2m and 2m. So we did 4m here and 4m here. And here we did 8m. So if we compare all these, we will see that we did 8, 8, 8. So we did 24m. Okay. And if we add all these, we will find we did 8, 7, 15, 6, 21, 21, 5 is 26, 30, 33 and 35. So we did 35m and here we did only 24m. So see, that's where we saved our operations. Okay. So again, if you let's say take another number. Okay. If instead we take this, we have L1, L2 and we have, let's say, L64. Okay. Total L64 lists. Okay. So in this, again, if you see in first level, how many comparisons we would do? We would do 64 comparisons, right? In second level, again, we would do 64 comparisons. Why? Because if you see here at all levels, we did 8m, right? Here 8m, 8m, 8m. And how many times we did 8m? Log of 8 times, right? Log 8 base 2 times. Okay, so similarly for this we will do 64 comparisons, but how many times? Log base 2 of 64 log base 2 of 64 is I think 6. Okay, so total number of comparisons we would do is 6 times 64, which is 384. Okay, but instead if we did something like this, what do you say, what did I say, total number of lists, k number of lists, and m, and if we keep on merging them one by one, what we would get? We would get 2m, 3m up to 64m, right? So if we find the sum of this, we will get 64 times 64 minus 1. I think the sum is n into n plus 1, right? N into n plus 1 by 2. These many operations minus m, because we have m missing here, right? So this many. So this is 32 times 65. 32 times 65, which is I don't know, 192 and 16, which is a lot. 208. I believe this number is right. Let me check in my calculator. Times 65 is 2080. Yes. So this is 2080 m operations, and here it was 384 m operations. So we have an optimization. If you see, if we merge two each instead of merging them one by one, we get an optimization. But what is wrong here is, I just noticed that this is not k times m. This is not m times k actually. If you see, this is k times we do the operation, but number of comparisons is a lot more than that. So I don't know how to calculate this, but you get the idea. Okay, you get the idea that we have an optimization if we perform the merging of something in the the way merge sort works. Merge sort also works like this. Okay, so if we do this type of merging, we will optimize on the number of operations. Okay, and also if you see, where did it go? As I said, n into k, which is less than 10 to the power 9. This might also be wrong here, because the number of operations is not like this. The number of operations is much more than just m into k. Okay, it is more than m into k. So what it is actually, let's try to find out. So if we have k lists, and if we keep on merging one by one each, so average size m, so the first merging is 2m operations, and the last merging is km operations, right? So basically this is sum of 2 to k, sum of 2 to k, which is basically k square, order of k square, right? Order of k square. So that's why the time complexity becomes order of m times k square. Okay, is m times k square order, because obviously when you sum this up, you will get k square by 2. Okay, k into k plus 1 by 2, but it is order of k square, right? So that's why order of m times k square. So I was wrong initially. It's m times k square, which we can optimize by using the other approach, and at that time it becomes order of m times k. Okay, it's not exactly m times k. What it is exactly, if you see, order of what we multiplied 6 and 64. So if you see, k times log of k times m. So basically, if you see, we optimized mk square to mk log k. Okay, so that's where we optimized. We changed k to log k. This is what we are going to do, and this is how it can be solved in the optimal manner. Okay. So for that, as I told you, we can merge L1, L2 up to Ln in groups of 2. But how will we Ln plus 1, let's say, but how will we or actually Lk minus 1 and Lk. Okay, how will we do that? We will do it in the same way we do in merge sort, the merge step of merge sort. But before doing the merge step, we do divide, right? We divide and conquer. So what we can do is, we have a list, right? So we have a list. We are provided with a method which we need to implement, merge k lists. Okay, and we have a list. We have a list of lists basically. Okay, so what we can do is, we can divide and conquer it. Okay, so we will divide and conquer. In this, we will take lists, we will take the start point, we will take the end point. So if the start and end are same, it means we have only one list, right? Start index and end index. If we have start equals to end, it means only one list. Okay, I'll change the color of my pointer. I don't know if it's readable or not. So if start and end are equal, it means there is only one list. Okay, so we can just return that list. If start plus 1 is end, it means there are two nodes. Okay, start index plus 1 is end index, means there are only two nodes. Then we can just merge them. Okay, as we discussed earlier, if we have here, we merge L1 and L2, right? We merge only two nodes. Every time we merge only two nodes. If we have more than that, okay, if we still move past beyond these 2 points, then what we will do is, we will find the mid. Mid is something between start and end, right? Start plus end by 2. Now, once we have our mid, what we need to do is, we need to again do divide and conquer from left to mid, and we will do the same thing from mid plus 1 to right. And once we do this, this will give us our answers, and eventually we will have we'll just merge them all. So if you see the dry run, that it will look like, it will be like this. So we have L1, L2, L3, L4, L5, L6, L7, L7 and L8. Now if you see, this is start, this is end, right? For start and end, we know that start and end are not equal, and start plus 1 is also not equal to end. So we will find mid. So when we find mid, let's say this is mid. Now for this portion, okay, so for this portion, now this is start and this is end. And for this portion, again, this is start and this is end. We do recursion, right? So again, if you see, we need to divide it more. So when we divide it more, we find that now we have this as start, because it will be divided here. This is mid, right? So this is start, this is end, and for this is start and this is end. Okay, similarly for this is start, this is mid, so this is end, and this is start, this is end. Okay, now you see, start plus 1 is equal to end, so we'll just merge L1, L2. Start plus 1 is equal to end, we'll merge 3, 4. Here again we will merge 5, 6. Here again we will merge 7, 8. Okay, then again if you see, for this is start, this is end. Again 2 nodes, start, end, means again 2 lists. So we merge again these 2, we merge again these 2. So we get L1, 2, 3, 4, we get L5, 6, 7, 8. So this is start, this is end. At every point we have only 2 lists and they are start and end, so we just merge them. Okay, so this is very clear. This is because this was power of 2, so it was clear. Let's take an example which is not a power of 2. Okay, so let's say we have L1, L2, L3, L4, L5. Now what do we do? So we have a start, we have an end. Okay, so what is the mid of these two? The mid of these two, let's say, is this. Okay, Now in that case, we split here. Okay, we say this is our start and this is our end. This is our start and this is our end. So there is no problem here. We just merge them and it becomes L45. Okay. Here, if you see again, it is start and end are not equal, and start plus 1 is also not equal to end. So we find the mid again. So again we split. Okay. And here if you see, we get start, we get end. Okay. So here we have start and end. So this becomes our L12. These merge and these become L12, and this is our L3. So now this is our start and this is our end. Again we have two lists and we can just merge two lists, right? So we just merge these two. So we have L123 and we have L45. So we merge L123 and L45 and we get L12345. So this is how this method will work even for the nodes which are totally not divisible or not in power of 2. Okay, I did not go into the basics of like how you will merge 1, 2, 4 and 1, 5, 6. Like I did not go into this step. Okay, if you want, I can go. Okay, I think I should go actually, because that will make the solution complete. So let's say you have two nodes, because the problem is now it's now boiled down to just merging two lists. So let's take the example of two lists and try to merge them. 1, 4, 6, one list, and we merge second list as, let's say, 2, 7 or 2, 3, 7. Okay, so what do we do is we compare first element of both the lists and we see whichever is smaller. Okay, so this is I, or let's talk about the pointers. Okay, so 1 and 2, which is smaller, we will just keep it like this. So also it would be better if I represent it in actually a list form. So L1 is 1, I forgot what the numbers were, but okay, 1, 4, 6, and L2 is 2, 3, 7. So we have pointers at starting point of both. Okay, so now we compare. If 1 is smaller than 2, what we do is we change the pointer of 1. Okay, we change the pointer of 1 to point to 2. Okay, actually it would be better if I write it like this: 2, 3, 7. Okay, so we change the pointer of 1 to point here. Okay, we change the pointer, but before changing the pointer we move it here. Okay, now 1 is pointing to 2, nothing is pointing to 4. Okay, actually I'll write the changed pointers like this. This is pointing here, this is gone now. Okay, or let's cross it, this is gone now. Okay, and before these things happened, the pointer has moved for the smaller one, because 1 and 2, 1 was smaller, the pointer from 1 moved to 4. Now if you see, now we compare 2 and 4. So when we compare 2 and 4, we see that yes, 2 is smaller. So in that case, what we did was we changed the pointer from 2 to 3. But since 3 is also smaller than 4, the pointer from 2 to 3 will not change. The pointer will remain as it is. Okay. Now we compare 3 and 4 and we see that 3 is smaller than 4. Yes, but before that, the pointer moves to, before we do anything, the pointer moves to 7. Okay. And since 3 is smaller than 4, what happens is the pointer from 3 moves to 4. The pointer from 3 moves to points to 4 instead of 7. Now you see we are still at 4, right? We are 4 and 7. 4 is smaller than 7. So now the pointer moves from 4 to 6, okay, to the next one, and it sees that yes, 6 is also smaller than 7. So the direction will not change. So it will remain as it is. Okay. And now while comparing 6 and 7, we find that yes, 6 is smaller than 7. So the pointer from 6, which is now pointing to null, will now point to 7. Okay. And now it is complete. So if we remove all the pointers which we just crossed, so this one and this one, we will find that this and this, you will see that the node that we get is, the list that we get is 1, 2, 3, 4, 6, 7. So this is how we merge two lists. We compare and just merge them. Okay. I hope you will be able to write code using the understanding of the algorithm that I discussed in this video. If not, then I have added the link of my solution in the description of this video. Please do watch that, but I would highly encourage to try this problem by yourself, and only rely on the solution if you are not able to achieve or if you're not able to write the code successfully by yourself. Okay, so yep, that's all, and as usual, thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.